We are live.
So hello, everyone. Welcome, young astronomers. Welcome, everybody who's joined us today. And today we have a very special session. Today is the first webinar from on the behalf of STEM&Space for the National Astronomy Challenge. As you know, many of you here today are already signed up for National Astronomy Challenge, and that's coming up in January. And for the next few months, you'll be with us and listen to the most exciting webinars and learn all kinds of new skills and astronomy through different sessions. So I welcome you again here. And let me now welcome our special guest, Professor Jayant Murthi. So glad to have you here today.
Thank you.
So I'd like to introduce Dr. Murthy. Okay, just 1 minute. So again, Dr. Jayant Murthi obtained his PhD from the Johns Hopkins University in the US in 1987. He was a National Research Council Fellow at NASA Goddard Space Flight Center for 2 years, and then a research professor at Johns Hopkins. He joined the Indian Institute of Astrophysics in 1987, where he is now a senior professor. Dr. Murthy works on the interstellar medium, which is the dust and gas between stars, and also builds instruments for space flights. The latest he's working on is a proposal to fly on the Chinese space station as part of a United Nations program. Welcome again, Professor Murthy. So today he will talk about space astronomy. So let's find out what is space astronomy. Space astronomy has revealed many new things about the universe. Today, Dr. Murthy will tell us about why we must go to space and some of the new things which we will learn. So welcome again. And we have a whole bunch of students who are waiting to hear your talk. So please go ahead.
All right, thank you. So let me just share my screen here. Okay, so everything's fine?
Yeah, everything's fine.
Good. So I'm at the Indian Institute of Astrophysics. I apologize for the background noise. It's raining quite hard here. Just started pouring. And so what I'll be talking about is space astronomy. Now, astronomy itself, or rather going into space, started, people had thought about going into space for a long time. You had Jules Verne from the Earth to the Moon. That was three selenonauts, as he called them, were shot from a giant cannon from Florida to the moon. They went there, they met various moon creatures, and then they came back. So in science fiction or in fantasy, we've been going out to space for a long time. But the real science of going into space started with Tsiolkovsky in Russia in the turn of the 20th century. And what he did was he was the first person to define the equations of spaceflight. After him, there came Goddard. Now, Goddard was an American, and what he did was he built liquid fuel rockets. Now you have the Goddard Space Flight Center of NASA. And in the time when he was working, 1920, it was still new and people were still unsure of whether rockets could fly or not. So here's a quote from the New York Times. After the rocket quits our air and really starts on its longer journey, it'll neither be accelerated nor maintained by the explosion of the charges. And so what the New York Times was saying in 1920 was that a rocket wouldn't work in space because it didn't have anything to push against. Now, of course, we know that, or Isaac Newton knew in the 17th century, that's not how a rocket works. A rocket really works because of the conservation of momentum, Newton's third law. Every action has an equal and opposite reaction. So how does a rocket work? A rocket works because you have a lot of hot gas inside the rocket. That hot gas goes out one end at high speed, and because of the conservation of momentum, the rocket goes in the other direction. And so the New York Times apologized in 1969 after Neil Armstrong was on his way to the moon. So it only took them about 50 years to apologize, which is much better than the Catholic Church took to apologize for the hounding of Galileo. Now, the people behind spaceflight was Wernher von Braun. He was a German, and he started with the V2 program. There were two of these so-called V programs from the Germans. I've forgotten what V stands for, but there were two of these V programs. V1, which was launching missiles on an aircraft, and the aircraft would go over and they would launch the missile and hit London. And the V2 rockets, which were self-propelled, they were launched from Peenemünde, the Peenemünde base, and then they came down and they hit London. And Hitler's idea here was that this was near the end of World War II, when it was clear that the Germans had lost. So this was a last-ditch effort to have to knock the British out of the war. And there's a famous lyric from Tom Lehrer: "Once the rockets are up, who cares where they come down? That's not my department," says Wernher von Braun. So von Braun was part of the Nazi program. And when it was clear that the Germans would lose the war, Hitler had ordered that the entire V2 program be killed. Not just the program be killed, but the people involved be killed. And so they had planned to send an SS death squad to assassinate von Braun and his team. So von Braun got to hear of this, and he led his team out, and they escaped in the middle of the night. They went through cornfields, they climbed over cows, and so on. And they gave themselves up to an American army unit. So the Americans didn't quite know what to do with them. So they captured them, and they took them back to the US, and they put them in Huntsville, Alabama, at what is now the Marshall Space Flight Center. And they told them, okay, you can work on your missiles, but you're working for us now. They didn't really want to put them front and center because these guys all had German accents. They had close cropped hair. The World War was just over. And so they wanted to keep them in isolation, a little bit inconspicuous. My classmate at the time was actually Wernher von Braun's son, Peter von Braun. Von Braun had died the year before, and his son was doing communication engineering at Johns Hopkins. Now we know that von Braun was not as innocent as he had said he was. He was actually involved in the Nazi program, and it seems quite clear that he knew that there was Jewish slave labor involved in digging the caverns under Peenemünde. On the Russian side was Sergey Korolyov, and Korolyov had a rather hard life. He was caught up in one of Stalin's purges, and so he was sent to the Gulag, and had quite a hard life there. And in fact, his life was ruined. His wife left him, and finally, in the war, he was rehabilitated, and Stalin brought him back to work on the Soviet space program. Of course, this was not just the space program, this was the missile program. And this is how Korolyov and the Russians sold it to the high command, sold it to the Politburo. They said that we're actually working on long distance missiles. Korolyov himself was never given due credit during the war. He was always, during his time, he was always called the great designer. Remember that this was the time of the Cold War, which I'll get into a little bit later. This was a time of the Cold War. And so the Russians were afraid that the CIA would try to assassinate him. And so never was his name mentioned. His people only got to know of his contributions after the collapse of the Soviet Union and the declassification of all of the papers. So he was the man behind the Russian space program. And so the space age started with Sputnik on October 4th, 1957. I'm going to be talking about space astronomy, but you can't have space astronomy without satellites. And so that was Sputnik. Sputnik itself was a football-sized object. And so all it did was it beeped. It did have a Geiger counter on board, but because of the Cold War and because of various reasons, they couldn't send any data down. So all it did was it beeped at people. It went around the world. As it went around, it sent out radio signals that anyone with a ham radio could get. Now remember, this was the Cold War. And so this is from a famous video called Duck and Cover, which was sent out to high school students everywhere, maybe elementary students everywhere. If you get a chance, watch it. It's on YouTube. And what they said in what they said in here is this guy is the hero. This is Bert the Turtle, and Bert the Turtle doesn't have to worry about explosions because he has his own shelter. Anytime there's a danger of an explosion, he ducks and covers. And so this is what they told students to do. They told students to duck and cover. Anytime there was an air raid siren, they had to hide under their desks. If they were not in school, they would have to go to their fallout shelter. If they weren't anywhere close inside, they would duck into a doorway or cover themselves with newspapers. Of course, we know now that none of this would have helped in the case of a nuclear attack. But this was the 50s, this was the Cold War. And so when the Russians launched this spacecraft, it was a huge deal. This was the front page of the New York Times. And along with Jimmy Hoffa, who elected Teamsters head. Later, Jimmy Hoffa was abducted and held hostage by criminals, but that was a later story. But the lead story was that the Soviets fired an Earth satellite into space. Now, what's important about firing an Earth satellite into space? If you fly an Earth satellite, then that means that you're sending a satellite up, which goes all the way around the world. If a satellite can go all the way around the world, then so can a then you can launch a nuclear bomb. If you're already sending something that goes all the way around the world, then you could easily launch a missile that goes and hits New York or Washington, D.C., or the Air Force Base in Colorado or Los Angeles. There's nothing that's safe from a nuclear bomb. And so what the Americans did is that, firstly, they went on a drive to, I'm sorry, this video won't show, I'll just go to the next slide. First, what the Americans did was that they went on an emergency program to go into space. So the first American satellites, they didn't want von Braun to do it because von Braun was a German and they wanted a true blue American to do it. So they asked the American Navy with their Vanguard program to launch a satellite. The Navy tried a few times, but they couldn't get any successes. And because they did everything in front of the press, after all, this was the Americans, and so they made a big deal out of this. They said the Russians are doing everything in secret, but we do everything in front of the cameras. So all of their failures were up in front of the cameras, and people watched these satellites try to go up and come down. So the press had a field day. They called these failures Flopnik and No Goodnik and so on. And so the first American success was with Wernher von Braun, with the Explorer program, which was actually launched from Huntsville, which was by Wernher von Braun and his team. And so one of the scientists there was James Van Allen, and he became. They had a Geiger counter on Explorer 1, so this was the first science done from space. And what this Geiger counter did as it went up, it went through some of what are now called the Van Allen belts after James Van Allen, and they discovered these belts of radiation around the Earth. So that was the first science done. Now, even after that, the Russians were still first in so many things. First came Sputnik, then came Laika, the first mammal in space, the first animal in space. And then after that came Yuri Gagarin, the first man in space, Valentina Tereshkova, the first woman in space, Alexei Leonov, the first man to walk in space. And so the Russians were first in everything. And so Kennedy, who was president when Yuri Gagarin when Yuri Gagarin went to space, he had to do something to show that the Americans were still ahead. So one of the things that they did was they put a lot of money into anything to do with science. So anything to do with space or anything to do with aerospace, or even in science in general, got a lot of money. And if you talk to many of the big scientists who came of maturity around that time, they'll tell you that it was a delta function. There was there was a very little money put into science before that, and suddenly after Sputnik, there was a lot of money put in. This again, as I told you, this came in the height of the Cold War. It was 12 years after the end of World War II. World War II, in many ways, was the physicists' war. It was won not just by the atomic bomb, which of course was a triumph of physics, but also other radar, LIDAR, all of these things came out of science. And so after World War II, science was suddenly a big thing. Physics was a big thing. And so there was a lot of money put into science. By the late 50s, now physics had started to take a backseat, and maybe other fields like biology had started to come up. But now Sputnik suddenly pushed anything to do with physics, or more specifically, anything to do with aerospace in front. So Kennedy said, we will, before the end of the decade, we will fly a man to the moon and bring him back. So the two things to note here. One is fly a man to the moon. Now this was, this Kennedy said because it was unconscious at the time. By man, he meant man. There were no women in science in those days, or very few women in science. The ones we know were truly exceptional. But certainly the astronaut program was dominated by men. It wasn't until Valentina Tereshkova that the first woman went into space, but even after that, neither in the American nor the Soviet programs were women a regular part of the space program. It wasn't until Sally Ride that women really started becoming a part of the space program. And even now, it's so entrenched that when the Gaganyaan program was brought in, they deliberately excluded women from the program. They said that only test pilots could become become an Indian astronaut, and if you were a test pilot, it's only recently that the test pilots were opened up to women. So clearly, no women could become part of the astronaut corps, and I felt that was an opportunity lost. But anyway, this was the 60s, and so the Apollo program came out of this Kennedy speech. Before the end of the decade, we will send a man to the moon and bring him back. Oh, the second thing I want to note is bring him back. And this is in contrast with someone like Elon Musk, who says we will send people to Mars and leave them there. They let them make their home on Mars. But be that as it may, the Apollo program went off. The Apollo 8 was the first manned program to go on the far side of the moon. And here are the astronauts, Jim Anders, Frank Borman, and Jim Lovell, who was later commander of Apollo 13. They were Time Men of the Year. And this is the canonical picture that they took. This is the Earth rising over the moon. And the importance of this is that this picture became a calling card for the environmental movement. Because you look at this, and you see the magnificent desolation of the moon, as Buzz Aldrin later said. And here's the Earth. This is all we have. We have no place else to go. When you see these billionaires talking about sending people to Mars, sending people out into colonies, you'll never do it. You can't send billions of people into space. The Earth is the only planet we have. And right now we're doing our best to ruin it. You can see by the unseasonable rains that we're having. You can see by the fires, by the droughts, the rain over Greenland. For the first time in recorded history, there's rain in Greenland instead of snow. There's no way that we're going to maintain that 2-degree rise in temperature that the IPCC has said. And so before we go out and colonize other worlds, the Earth is the only world we have. And so the Apollo program culminated with Apollo 11. And this is Buzz Aldrin saluting the flag. Neil Armstrong was the first person on the moon. That's one small step for a man, one giant leap for mankind. But there's very few photographs of Neil Armstrong on the moon because Buzz Aldrin liked being in the picture. And so Neil Armstrong took all the pictures and Buzz Aldrin was in all the pictures. So very few pictures of Neil Armstrong on the moon. Of course, many people will have heard about the moon hoax. And I never talk about it because there's so much good science in the world that why should you talk about bad science? So whenever anyone asks, I just point everyone to this site, badastronomy.com. And that goes through all of that all of those conspiracy theories and shows why they're all junk, why the program is an hour-long piece of junk. Now, the one thing that I was interested in, I can only, Sherlock Holmes once told Watson had just told him that the Earth went around the sun. And he said, well, Watson, thank you for telling me that. But now that you told me, I'm going to do my best to forget it because I can only remember so many things. And so I only like to remember interesting things. And one of the things that I found interesting was why the flag looks like it's waving. And this is one of these conspiracy things. If the flag was waving, well, then there must be a wind. And if there was a wind, then obviously it was filmed in Area 51. But if you look at these two pictures of Buzz Aldrin, and I hope the blinking is coming through, then you'll see that the astronaut, Buzz Aldrin here, in this one, he's saluting the flag, and then he has his hands by the side. So you see that the perspective changes, but the flag, the waves in the flag don't change. So the reason the flag looks like it's waving is because there was a spring to extend the flag. And that spring broke. I mean, things in space are hard. So that spring broke and the flag didn't extend out all the way. So because of that, the flag looks like it's waving. And NASA likes the look because a flag should look like it's waving. And so on all future missions, they deliberately set the flag to look like this. All right, so far I've told you about the background. This is one of the reasons to go into space is just politics. Apollo 11 was all politics. The idea was to put someone on the moon first. After Apollo 11, interest in the Apollo program pretty much died. And the last mission was Apollo 17, where actually there was a scientist on board, the first scientist, Harrison Schmitt, who went and brought back most of the rocks that are now in museums all over the world. So that's one of the reasons, pure politics. Now here's another reason to go out into space. It's because if we send satellites up, we can observe the climate. We can observe weather. And so here's a picture of 5 cyclones off of the eastern coast of India. Now, this is clearly important. It's important for fishermen. It's important for farmers. Important for disaster management. You should know if you should know what the weather is. And everyone has seen these pictures of clouds coming in from satellite maps. So that's one of the benefits. Another benefit is remote sensing. One of these buildings is my house. I won't tell you which one, but one of the buildings is my house. And so it's important in things like mapping. You can map the tree cover. You can see how the forest cover is changing. You can see how land use is changing. You can see where the fish are. You can see where rice is being grown, where wheat is being grown, and so forth. So you can do a lot of work from space, and there are in fact companies that do this. They look at space. They look at remote sensing images, and they sell them. Planet Lab is one of these. Other reasons, global telecommunications, although perhaps that's less important with all the fiber that we have. Military applications, it's easier to send a spy satellite over. GPS has become crucial to our daily lives. We can't live without having GPS so that the delivery guy knows where to come, or the taxi knows where to pick us up. We know where to drop us, and weather forecasting and remote sensing. So these are all commercial reasons to go into space. Now, there's no reason to justify these. These will be justified just on their own. Everyone wants to make money, and so they go out into space to make money. All right, that's fine. But that's not what we do. That's not what I do. What I do is astronomy, basic science, pure science, blue sky science. And so you have to ask, why do we do science at all? Why is science important? And so everyone will have their own answer. One of the common answers you see is that the science of today is the technology of tomorrow. If it wasn't for who was it, Becquerel and his X-rays, we wouldn't be able to set bones. If it wasn't for Towns and lasers in Bell Labs, we use lasers everywhere, from the computer that I'm giving this talk on, to laser eye surgery, to your supermarket. Lasers are everywhere, and these all came out of basic science. So that is the obvious answer. But I personally think that's cheating, because what I think is important is that we do science not because we think it's useful, but because we want to learn about the universe around us. We do it for curiosity. And as a hidden agenda, we teach rationality. Science has a cause and effect. Nowadays, we hear so many things. We do things not because they're rational, but just because someone tells us that way. And we know that the sun rises because of science. It doesn't rise because we do our daily puja. It rises because of science. And so this is what we do with science. We teach rationality. Once you think about it, you go ahead and do what you want, but at least be aware of why you're doing it. And this, of course, applies to the broader world. Once you see that rationality applies in science, well, of course, it'll apply everywhere. And you can't, the modern world is built on science. Again, to go back to GPS, it wouldn't work unless we knew how relativity worked. You have to correct for both special and the general relativity if you're to know where you are. So that's why science is important. And so let me have this bottom point, which is that I think it's important to do curiosity-driven research. And you may come up with your own ideas on this, but I think it's important that every nation spend some part of its budget on curiosity-driven research. In India, the total science budget is something like 0.7% of the GDP. In China, which has a GDP 5 times or whatever larger than ours, they spend 2% of their budget on the GDP. It depends. In Israel, I think it's closer to 4 or 5%. So these countries spend a lot more money on research, and the research does give back to society and to the economy. We just need to, in many ways. Now, once we accept that research is expensive, and once we accept that research is justified, that scientific research, that blue sky research is justified, Then we have to ask, why do we want to go into space? Now, going into space is expensive. Many reasons. Here's the fused rocket, which is blasting off into space from Cape Canaveral, if I remember right. And you can see clearly that's money there. You're launching this huge rocket. Most of that bulk is stuff that doesn't even go into your payload. Out of this whole payload, out of this whole rocket, your payload is just a little bit on the top, and maybe a few hundred kg. And once you send it up into space, well, then the lifetime is limited. You can't go fix it. If you make a mistake, that's it. Your instruments are whatever the instruments were at the time you launched, not even at the time you launched, well before the time you launched, because you want to send up only things that you know work. The motto for space flight is keep it simple. Don't do anything tough, just keep it simple. And when people there have been so many cases when things have just gone wrong. I remember a rocket flight done by one of my previous graduate students at Hopkins. What they wanted to do was to observe the sun during an eclipse. And so they pointed the rocket to the brightest object in the sky, because the sun is the brightest object in the sky, except in an eclipse. In an eclipse, the Earth is the brightest object in the sky. And so instead of getting the sun, they managed to get some nice pictures of the Earth atmosphere. There was another student-built spacecraft, Terriers, where they made a sign mistake. Instead of a +1, they put a -1. And so the spacecraft, once it was launched, instead of pointing towards the sun, it pointed away from the sun. And so the batteries wouldn't charge, and they ran out of power within a few hours. The Wire spacecraft, Wire, I think it was, it had cryogen on board, but they opened the lid 3 minutes into the launch instead of 3 days into the launch. And so all the cryogen boiled out, and they were operating at 200 degrees Kelvin instead of 10 degrees Kelvin. So things happen, mistakes do happen. And once they happen, there's nothing you can do. Once your spacecraft dies for whatever reason, maybe your power supply dies, maybe your detector stops working, whatever it is, you can't fix it. And so why do we go into space? So one of the reasons is because what we can observe from the ground is only a very small part of the whole electromagnetic spectrum. All we can observe is this visible sky here, and then we can observe out into the long wavelengths radio. In my own field of UV astronomy, we can't observe from the ground because the sky will block it. X-rays, gamma rays, microwaves, we can't observe in any of these because the atmosphere will block it. Now, the reason that we want to look in these other wavelength ranges is because the electromagnetic spectrum is simply dependent on the temperature. It's a reflection of the temperature of the object. You know that the highest energy objects will have the highest temperature. Temperature is a measure of how fast things move. So when things are very hot, they'll move fast, they'll have a high energy. When things are very cold, they don't move, they move slowly, and so they'll have a low energy. So the highest energy objects are the highest temperature objects. The lowest energy objects are the lowest temperature objects. So energy is just wavelength. So the highest energy photons are the shortest wavelengths. The lowest energy photons are the longest wavelengths. So when we look in gamma rays, which is the short wavelength of the spectrum, we see the highest energy objects. When we look in the radio, which is the longest part of the spectrum, now we see the coldest objects in the universe. So in gamma rays, we see things like supernova remnants, black hole accretion disks. When we go to the radio, what we see is the leftover radiation from the universe, the 3-degree microwave background. And when we look in our own galaxy, we see this in effect. So if we look at the coldest parts of the universe, at the longest wavelengths. What we see are the radio is are things like molecular gas, molecular dust, molecular gas and dust, because those are temperatures of 20 degrees or maybe 60 degrees Kelvin. As we go to shorter and shorter wavelengths, once we get to the visible, we see the optical sky. And then in the X-rays, we see basically black hole candidates, Cygnus X1, Scorpius X1. You also get more from looking in multiple wavelengths. If we look in the optical, we see these dark patches running through the plane of the Milky Way. This is dust that's blocking the light of more distant stars. If we then go to the infrared, we see that light, the light that was absorbed in the optical is then re-emitted in the infrared. The optical, the dust absorbs the light of the distant stars, and then it re-radiates that light in the infrared. And so you see that the dark patches in the optical, like this is the cold sack here, is a bright patch in the infrared. So that's one reason to go into space, because we see other wavelength regions. Another reason is because the sky is bright. If we go out, I live in Bangalore, and so in Bangalore, if you go out, you can just barely see the brightest stars in the sky. If you go out to a remote area, to the villages somewhere, the sky is so much darker that you won't even recognize the constellations. But even in the darkest places on the Earth, the mountains in South America, Hawaii, the sky is no fainter than about 23rd magnitude or so. And I'll explain in a second what that means. But here's a practical observation from the space station. So just take the camera and point it out. And here is Orion, and here's the Earth's atmosphere. So you can see the difference between the Earth's atmosphere and not the Earth's atmosphere. And the final reason to go into space is because of twinkling. When you look out in the sky, when you look at a star, the star twinkles. The reason the star twinkles is because there's so much air between us and the star, and that air has all these microcurrents in it. So the density and the index of refraction is constantly changing. And so because the index of refraction is constantly changing, the position and the brightness of the star appear to change a little, and the star looks like it flickers. And the net effect is that anything when you look from the Earth is blurred. So here, from a 2-meter telescope, the McDonald Observatory, is this galaxy, NGC 4313. And all that you see in the center is a blur. When you look at that same blur with the Hubble Space Telescope, now this is in the optical, not in a different wavelength range. Even in the optical, you now see that there's a ring of star formation around the central dusty disk. And so just by going into space, you can see things so much clearly. I don't know how many of you wear glasses, but it's like me taking my glasses off. If I take my glasses off, I can't see any detail at all. Then I put my glasses off, and suddenly the world is sharp. So we go into space for these reasons, new wavelength reasons. We can go out into X-ray or UV instead of just the optical. We're free from the sky brightness. And again, because of the atmosphere, we don't have to worry about all the twinkling. So the first science from space began even before Sputnik, even before Explorer. It began with sounding rockets in 1947. So the Americans had captured these V2 rockets from the Germans. And with these captured rockets, they sent them up, and they were able to take pictures from out of the Earth's atmosphere. So they were able to catch the first spectrum, the first observations of many objects in wavelengths other than optical, in the UV, in X-ray, in gamma ray, and so on. So this is a UV picture of the sun. The other advantage of rockets is that rockets are fast. So you can develop them and reasonably cheap. Within $1 million, within a year, you can develop a rocket flight. And so if you know that a comet is coming, there's no way you could send a satellite up to observe the comet, but you can send a rocket up. And so rockets are used now. In the early days, they were used to discover things. But after all, you can only observe so many things for the first time, once. And so after that, then you observe it for the second time, third time. It doesn't make that much of a difference. So now sounding rockets are used largely for instrument development You don't want to send something up on a satellite for the first time because you never know what can go wrong. So you send it up on a rocket to prove that it works. Once you show that it works, then okay, then you can send it up on a satellite. And as another important thing, and this is what we use, we develop in my lab, we develop rocket instruments for space, but we do it on a fairly low budget, so that we do it for low cost instruments, and then they can go with those abilities that they develop, and they can go and work on more expensive rockets and satellites. Now, the satellites, most of them have come from NASA. And so you can go to the NASA website and look at all their missions. And I would encourage those of you who are really interested in science to go there and click on any of the missions that they launch, that they've launched. NASA has one of these, they realized in, I think, the late 90s that their people were retiring and not enough people were coming in. So they launched a program to try to bring people into science. This is the STEM program: science, technology, engineering, mathematics. And Sally Ride, by the way, she was heavily involved in bringing women into STEM, but they wanted to bring people into STEM. And so they had a good education and outreach program. And so each of these missions had to have a dedicated education and outreach. And so you can go to any of these missions, click on them, and they'll explain in terms suitable for anywhere from kindergarten to 12th grade and higher what they did and how they did it. And so now I'll just go through a few of the highlights from space, just to end up. So one of the ones was COBE, the Cosmic Orbiting Background Explorer, which resulted in 2 Nobel Prizes, one for John Mather, who is now the chief person behind the James Webb Space Telescope. And the other was George Smoot, who you may have remembered from the Big Bang Theory. So this was one of the instruments, FIRAS. And what it showed is that the universe is a black body. The universe has a temperature of 2.725 degrees Kelvin. And what that means, don't worry about a black body, just it's just a way to measure the temperature of the universe. So what this means is that if the universe is a black body with a temperature of 2.725 degrees Kelvin, that means that it originated in the Big Bang. Before that, there were other ideas, possibilities, maybe things like steady state theory and whatever else. But after COBE, the only tenable explanation for the beginning of the universe is the Big Bang. So this showed that the universe started in a Big Bang. And this won a Nobel Prize. And I was at the meeting where it was announced, the American Astronomical Society meeting in Washington, DC, and it got a standing ovation. This is the Eagle Nebula. And so what you will see here are these red stars. These stars are actually not red stars. They're actually bright blue stars. The reason they look red is because you're looking at it through so much dust. And so the dust reddens the light from those stars in the same way that the sun is reddened when you looked on the horizon. A little more complicated, the sun's light is actually reddened because of the Rayleigh effect, because of gas molecules. But also, if there's a lot of dust in the atmosphere, you'll see that the sun's light is especially reddened. And so this is dust reddening. So what these are stellar nurseries. These are places where stars are being born. So here you're looking at these huge clouds of gas and dust, but you're also looking at baby stars. Our sun once started in a place like this. Another of the instruments on the Space Telescope is the STIS instrument, the Space Telescope Imaging Spectrograph. It's a long slit spectrograph. And what they did was that they put their slit along this galaxy, M84. The center of the galaxy is at the center of the slit. And so as you go to the top, what you see is that the light is neither red shifted nor blue shifted. As you get closer to the center, suddenly the light becomes heavily blue shifted. Blue shifted means that the stars are coming towards us very fast. The light is blue shifted, same way that an ambulance siren, the sound becomes higher pitched as it comes towards you. And then you go through the black hole in the center, and then the light is redshifted as you go away. And so what this shows is that at the center is some huge amount of mass, because you have the stars coming towards us very fast, you have the stars going away from us very fast. Because you know how fast they're moving, you know how much mass is in the center. This is just Kepler's laws, same laws that apply to our solar system. And you can measure how big an area that, or how big a volume that's in. So you know how much mass is in this little volume. Only way you can have so much mass in such a small volume is if you have a black hole. And so here, I know you're not actually seeing the black hole, but you are seeing the black hole. This is what a black hole will look like. And again, let me skip that. Let me skip this. So one of the instruments that hasn't flown, but with the LIGO results, is now got new life, is the LISA instrument. Now LIGO is searching for gravitational waves from the ground. But when you're doing it from the ground, you can only do it over a limited number of frequencies, because your your distances can only be on the order of kilometers. But if you go out into space, now you can put your spacecraft thousands of kilometers apart. And as long as you measure the distance very precisely, anytime a gravitational wave goes by, you can measure the gravitational wave. So this is just LIGO in space. Here you have something from the global surveyor in Mars. And what you have here is two images from 1999 and 2005. And so if you look at the image on the right, what you see is that there's a shiny patch, which turns out to be water ice. Now we know that there was lots of water on Mars in the past, because if you look at this canyon, you can look at the erosion channels on the canyon. But even more than that, you now know that there's a lot of water on Mars even now, because you're seeing this, this water ice, this icy patch on Mars. Okay, and let me go through this, just this one last thing, and then finish up. And so one of the things that we've seen is there's been enormous progress in exoplanets. That is, planets that are outside our solar system. And this was the first of the missions, was Corot, but that's been superseded now by Kepler. And so what Kepler did is it looked like for Earth-sized planets around sun-type stars. And so you look for eclipses. You look for the planet in the same way that the moon goes in front of the sun, or Venus goes in front of the sun. There'll be a small diminution in the light of the star as you look at it. And so here you get an eclipse. And so that's all that Kepler did. It looked for eclipses. And so now most of our exoplanets have been found by Kepler. Kepler, we now know that every star will have planets. There's not a single star without any planets. And it's found a whole variety of planets, everything from hot Jupiter-sized planets that are orbiting closer to the sun than Mercury is, to not exactly Earth-type planets, but planets which may be Earth-like, which may fall within the habitable zone, which may have life. And so, so that's there. All right, now let me end up with just just a small discussion on this paradigm shift in astronomy that's happened. And a lot of this is due to space astronomy, because what happens? Space is too expensive for people to own data. In the old days, you would go to a telescope, you would take a photograph, and you would put that photograph in your desk. But once you launch space missions, now space missions are expensive. And so now you understand that I can't launch, not everyone can launch a space mission. And so now it's wasteful to give the data to one person. So what the paradigm is now is that the data are now the property of the public and not the observer. So almost all astronomy data is available on the web. Whether you can use it or not, that depends on, it's got various, the learning curve may be steep. But nevertheless, in principle, all the data are available. We now have fast computers, fast internet. Scientific results are publicly accessible. In the old days, if you wanted to look at the latest results, you had to go to a university. But now all the results are also publicly available. And so now we have this paradigm shift where anyone can get involved in astronomy research. And so one of the models of amateur astronomy is that people take a telescope and they look out at the sky, and they do things like observe the Messier objects, or they observe Saturn or Jupiter or whatever. But now this opens up another way to do it. I was never very much interested in that. I was always more interested in learning why things work and how things work. And so now you can get data from any mission. You can download it to your computer and you can look at those data, and you can learn about what people are doing. So let me end there, and happy to take any questions.
Thank you so much, Dr. Murthy, for that really great talk. You started all the way from the beginning of space exploration to where we are currently. And as you said, citizen science even is growing rapidly because all of us can access data, and we have so many data analysis tools. Yeah. And thanks for sharing the image of the moon mission debunking, because a lot of students always have questions about that. So yeah, let me mention some of the questions. Of course, there are a lot of questions, but I'll bring a few across to you. So Tanvi asks, what is the meaning of FIRAS data? If you can just say it in a couple of lines, and maybe
the FIRAS data.
More. Yeah.
So the FIRAS was one of the instruments, far infrared something. One of the instruments on COBE. And what it did was it took on the Cosmic Orbiting Background Explorer mission. And so what it did was it looked at the intensity as a function of wavelength in the infrared. Now, the infrared is where you would expect the microwave background, the universe, the radiation from the universe to come from. And so that's what it did. It measured the background radiation from the universe. Actually, this was quite a difficult task because you have to look at it. You're looking at things which are a temperature of 2 degrees, and you're looking at it through our entire galaxy, through the solar system, through the galaxy. We have the zodiacal light, which is at a temperature of 100 degrees. So extracting all of that is very difficult. And so that's what FIRAS did first. It extracted the background, the temperature of the background, the spectrum of the microwave background from which you get the temperature.
Yeah, thank you for that. And I don't know if you remember, but actually I worked on the COBE mission too, on the Derby.
Oh yes, of course. Of course.
So yes, so that's one reason I brought up that question. So let me.
Which also got the Nobel Prize. Derby also
got
the Nobel Prize, yeah.
Yeah. And so Archana Singh asked, how was the picture of the black hole taken?
Okay, I mean, what I showed was not actually a picture of a black hole.
Right. Yeah.
What I showed was the spectrum of the stars around the black hole. So as you look at the stars that are orbiting, and I'm sorry, I have a video, but it didn't play. As you look at the spectrum of the stars around the black hole, when you look far from the black hole, the stars are just going slowly. As you get closer and closer to the black hole, and you can think of this in our galaxy too, as you get closer and closer to the black hole in the center, the stars are going faster and faster. And as you go through the black hole, now they go from rapidly going towards us to rapidly going away from us. And so that's what you're seeing. You're seeing the velocities of the stars. You're not actually seeing the black hole, but you're seeing the velocities of the stars.
Right. Dr. Murthy, can I just request you to close the presentation? Then
sure.
We can see you full screen.
Sure.
Or stop the sharing.
Stop share. Yeah.
Right.
There we go.
Okay.
Yeah.
Thanks. And you ended up talking about Kepler and of course TESS after that. So one of the questions is, can you tell us a little more about exoplanets and yeah, can you tell us a little bit more about exoplanets and how what research is helping us, how that research is helping us?
Fascinating field, and I wish that if I were starting out now, I might very well have gone into exoplanets rather than, because so when I was a graduate student, there were no planets other than our own solar system. The first planet was discovered, I think, in '87, was it? And just around the time I finished my PhD, and so. The Nobel Prize last year, by the way, 2 years ago, was given to 2 years ago was given to Meyer and I'm blanking out.
Yeah, I'll just check on.
Yeah, but it was given for the discovery of planets. John Bacall and Meyer and okay. Anyway, so the first exoplanets were started to be discovered in the 1990s. And by the time of the turn of the century, there might have been about 200, 300 planets discovered. But most of these planets were Jupiter-sized planets. There were big, hot planets that were very close to the sun. They were not Earth-like planets, so very unlikely to have life there. So now what happened in the, so then people said, okay, well, let's start to look, let's go out into space so that we can do better. And let's not look for the way that planets had been found before were because of radial velocity. So as the star goes around, as the planet goes around the star shifts a little bit, and you detect the blue shift and the red shift of that. So now the way that Kepler does it is it looks at eclipses as the planet goes in front of the star, and using that method is more sensitive and it's better, and it's so you find smaller planets. And so what they've done now is that, as I said, they found 5,000 plus planets. And these planets range from all types. You have these super Earths, you have whatever they call them, super Neptunes, hot Jupiters. They've even discovered moons using Kepler data. Right. And I should say here that a lot of this stuff has been found by citizen scientists. They had a website, planethunters.org. And using that, people could go there and they could search for planets for themselves. And Tatooine, for instance, the planet with 2 suns, that was found by a citizen scientist. So the great thing about Kepler, or what the paradigm shift again from Kepler, is that now we know that planets are not unique. We know that solar systems come in all types. They're all different types of planets, all different types of solar systems, all different types of orbits. And so now we know planet. When I was a graduate student, it was still an open question. Are there planets anywhere else? Now we know that that's not a question. Now we know there are planets. So now we go on to the next step. So things like TESS, they start looking for Earth-like planets and and maybe life signatures of life, maybe things like oxygen, water, things like that.
Yeah, thank you. So you mentioned the JWST coming up. So would you like to tell us a little bit more about that?
Sure. So JWST is one of these missions. It's been long delayed for a variety of reasons, but it's so ambitious. They're launching a 6-meter telescope, I think, into space. 6 meters is huge. So the only way they can launch it is they launch it in a butterfly shape. The telescope opens up once they go into space. And they send it out to one of the Lagrangian points. I always get them mixed up, L1, L2, whichever it is. And so this is far away from the Earth. It's one of these semi-stable points. And so the reason you send it out there is because JWST works in the infrared. If you're near the Earth, now you're working against the high temperature Earth background. The Earth itself has a temperature of almost 300 degrees Kelvin. As you go out further, you're still hot. So you want to go as far from the Earth as possible, so that you're in a very cold environment. So they're going out to L1. And what they will do is they have 2 main science goals. One of the goals is to look near the edge of the universe, because as you go out to the edge of the universe, of course, things are very redshifted. And so you'll see them at these long wavelengths. And the other reason is that, and the other thing they want to do is they want to look for planets. And so because you're going out with, because you have a 6-meter telescope, you're able to get that much more resolution. You're way out in space, able to do that much fainter. And the infrared is where you really want to look for planets, because the star is faintest in the infrared, the planet is brightest, just because the planet is at a temperature of about 100 degrees or so, the star is at a temperature of 5,000 degrees. And so, so that's what JWST will do. It'll look for planets, and it'll look for the edge of the universe. But JWST, I should note, is not a discovery mission. It's not a mission which will go out and discover new planets. Rather, you look at planets that you've already found, and you get so much more information about it.
Right. Yeah, so we're all looking forward to JWST, because that will be in the next few months, by the end of the year, I guess.
We hope so. We hope so.
Right. Yeah. And similarly, I want to point out that in the beginning, you said that they were all men in these missions. And now Artemis is aiming to take in more women and more of a diversity. So again, hopefully we'll see more and more diversity in space explorers.
Absolutely. But you know, what really struck me, if you remember, they were going to have in Women's Day 3 years ago, they were supposed to have an all-women space flight.
Right.
And it turns out they didn't have enough space suits.
And that's right. I remember that. Yeah, it didn't fit the woman.
Yeah.
So yeah. So thank you for being with us today. And it was very exciting. And I hope all our students, we have a large range of students. So I hope our students understood how space exploration started and where we are going. And thanks for giving us a background of this whole information. And from our side, thank you so much for joining us today.
My pleasure. And I hope the students will keep learning more.
Okay, thank you. And students who have joined us, again, National Astronomy Challenge, even for Dr. Murthy, it's like an Olympiad challenge that we are doing in January. But meanwhile, we don't want it to be a one-time Olympiad. So students will be, for the next 4 months, will be engaged with us, be part of webinars and some learning. So they get to learn about astronomy and, for the next few months. So a lot of them here today are just starting on this journey. So everyone, welcome. And we will have a session soon on how to spot objects in the night sky. So thank you again, Dr. Murthy, for starting us off, and great to have you with us here today.
Thank you.
Thank you. Bye. Everyone. So that was great to have Dr. Murthy here with us today. And as I mentioned, for students who are still online, our next session will be What's in the Night Sky, Spotting Planets and Constellations. So that's what we are looking ahead for, and we'll let you know about that. Thank you.